Hello everybody, my name is Ananya Kantraj. So today I'm here with another subject, analysis and design algorithms. So today's topic is about insertion sort with time efficiency. So let's look into the index. So the contents includes the introduction to insertion sort, the logic of the insertion sort, algorithm of the insertion sort, and an example of an insertion sort, and time efficiency of an insertion sort, and the applications and conclusion of insertion sort. So, what do you know about an insertion sort? It's nothing but simple sorting algorithm which builds a financial sorted array one item at a time. So it's efficient for a small data set, but not as efficient as more advanced algorithms like merge sort or quick sort for larger data sets. So it's nothing but it has a simple algorithm and it's iterative approach. It's nothing but it works by building the sorted array one element at a time, iterating through the input array. Third is that in-place sorting is present in the insertion sort. But insertion sort sorts the array in place, meaning it does not require any extra memory other than array itself. And it's stable sorting algorithm. Compared to other sorting methods, I think one of the best stable sorting method is or the algorithm is the insertion sort. And efficiency, insertion sort is efficient for all the small data sets. Then what are the advantages of insertion sort with time efficiency? Its primarily lie in specific scenarios where its characteristics provide benefits in terms of time efficiency. So efficiency for nearly sorted data. Insertion sort performs exceptionally well when dealing with data sets that are already partially sorted or nearly sorted. So its time complexity in such cases approaches O of n, making it highly efficient compared to other sorting algorithms. So small data sets in scenarios where the data set is small, insertion sort can outperform more complex algorithms. So what are the disadvantages of insertion sort with time efficiency? So first is the quadratic time complexity. So in the worst case scenario, the insertion sort has a time complexity of O n square, where n is the number of elements in the array. This makes it inefficient for large data sets as the time taken to sort grows quadratically with the number of elements. Inefficient for large data sets too, which is one of the major disadvantages of using insertion sort. So because of its quadratic time complexity, insertion sort becomes inefficient as the size of the data set increases. For every large data sets, other sorting algorithms like merge sort or quick sort, which have better average and worst case time complexities, they are more suitable. Coming to high sensitivity to initial order, which is yet again a disadvantage, it's nothing but insertion sort's performance can vary significantly based on the initial order of the elements. So if the elements are already nearly sorted, then insertion sort performs efficiently with a time complexity closer to O of n. But if the elements are in reverse order or in a random order, then it performance degrades gradually. So the fourth is that it's not suitable for linked lists. So insertion sort works efficiently on arrays but can be inefficient when used with linked lists due to the need to repeatedly traverse the list to find the insertion point for each element. So other algorithms like merge sort and quick sort are more suitable for linked lists. Then comes not suitable for large data sets like while insertion set is stable, it preserves the relative order of equal elements and performs well for small data sets or nearly sorted arrays. So its stability may not be, significant advantage for very large data sets where time efficiency becomes more crucial. And the logic of insertion sort, it's as follows. Iterate through the array as the first step, but with this, you start with the second element of index 1 of the array and iterate it through each element from left to right. Second is select the element to insert. For each element in the array, consider it as a key element that needs to be inserted into its correct position within the sorted subarray to its left. The order is to compare and shift. Compare the key element with the elements in the sorted subarray to its left. Move each element in the sorted subarray that is greater than the key element one position to the right, and insert the key element, which is the fourth logic. When you find the correct position for the key element, that is the element in the sorted subarray that is less than or equal to the key element, insert the key element into that position, and then is to repeat. So continue this process for each element in the array until the entire array is sorted. So let's look into the algorithm for the insertion sort. So start with the second element key in the array. So compare the key with the elements before it, before it, before starting the second element as a key in an array, you got to compare the key with the elements. If the key is smaller than the elements, then shift the greater elements to, one position to the right to make space for the key. Repeat the, second step and the third step under the correct position for the key is to be found, and insert the key into the correct position until you find the correct position of the required key. And then move the next element in that array and repeat the steps 2 to 5, which is mentioned over here, until the entire array is sorted. So here you can look into the algorithm once. So input is nothing but an array of non-triple elements, and the output is nothing but array sorted in non-descending or decreasing order. So insertion sort is nothing but for I is equal to 1 to length array minus 1. You're going to insert a key which is equal to array of I. And then we insert an element j which is equal to I minus 1, while condition is used here while j is greater than or equal to 0. An array of j is greater than key. We're going to insert array as j plus 1, which is nothing but array of j, or else j is equal to j minus 1, and array of j plus 1 is equal to the required key. So let's look into an example of an insertion sort. So let's consider an array with the square brackets containing the elements 5, 2, 4, 6, 1, and 3. So we'll go to the step-by-step through the process of sorting this array using insertion sort. So initial array is 5, 2, 4, 6, 1, and 3. So first pass, I is equal to 1, key is equal to 2. So we start with the second element, key is equal to 2. Since 5 is greater than 2, we shift 5 to the right to make space for 2. Okay. So next array up to the first pass, the order is 2, 5, 4, 6, 1, 3. Second pass, I is equal to 2 and key is equal to 4. We move the third element since 5 is greater than 4. We shift 5 to the right to make space for 4. That's how it's done here. So similarly, since 2 is greater than 4, we shift 2 to the right to make space for 4. The 2, 4, 5, 6, 1, and 3 is the array up to the second pass. Now, the third pass looks like I is equals to 3, but the key is 6. So we move the fourth element, that is the key is 6. Since 5 is less than 6, 6 stays at that same position. The array after the third pass is nothing but 2, 4, 5, 6, 1, and 3. Fourth pass is nothing but I is 4, key is equal to 1. So we move the fifth element, which is nothing but key is 1 here. So we compare 6, but it is greater than 1 here. So we shift to the right, that is nothing but 6. So similarly, we compare 5, which is greater than 1 yet again. Finally, since 2 is also greater than 1, we shift 2 to the right. So what happens here? 1 comes to the first position after the fourth pass. Second is in 2, 4, 5, 6, and 3. Now let's look for the fifth pass. We are remaining with key is equal to 3. So now I is equal to 5 and key is equal to 3. So we move to the sixth element, which is nothing but key is 3. We compare 6 with 3, which is greater, and shift 6 to the right. And then we compare 5, which is greater than 3, and shift 5 to the right. And finally, since 4 is greater than 3, we again shift 4 to the right and insert 3 in the correct position. Now, after the fifth pass, it is 1, 2, 3, 4, 5, and 6. So array is sorted and the array now it's sorted in ascending order. So the final sorted array using insertion sort is given as follows: 1, 2, 3, 4, 5, and 6. Okay, so what is time efficiency of insertion sort? The time efficiency of insertion sort is influenced by the size of the input array and the initial order of the elements within the array. So here's the breakdown of the time complexity. The first is the best case. If the array is already sorted or nearly sorted, insertion sort performs quite efficiently. In the best case scenario, the time complexity is O of n, where n is the number of elements in the array. It's because for each element, only a constant number of comparisons and shift are needed to insert if into the correct position. Now, the worst case is that where the array is in reverse order. Insertion sort is highly inefficient. The time complexity in the worst case is O n squared. That's nothing but n is the number of elements in the array. It's because for each element, it may be needed to compare and shift it with every element in the sorted subarray to its left. Average case is nothing but the insertion sort's time complexity is also O of n squared, making it inefficient for large data sets compared to more advanced sorting algorithms like merge sort or quicksort. Now, space complexity. Insertion sort has a space complexity of O of 1 because it sorts the array in place, meaning it doesn't require additional space proportional to the size of the input array. So let's look into the applications of insertion sort with time efficiency. The insertion sort, despite its simplicity and relatively slower time complexity compared to some other sorting algorithms, finds its utility in various scenarios and applications. So especially when dealing with small data sets of situations where simplicity and stability are valued over a raw speed. So here are some of the common applications of insertion sort. So first is a small data set. Second is nearly sorted arrays. So the small data set is nothing but insertion sort is efficient for sorting a small data set or arrays with small number of elements, as we saw in the example. So in such cases, what happens is that its simplicity and ease of implementation can outweigh its slower time complexity. So when it comes to nearly sorted arrays, when the input array is already nearly sorted, insertion sort performs quite efficiently. So its time complexity approaches O of n in such scenarios, making it a suitable choice. Then looking into the other part of the insertion sort is nothing but the conclusion. Here we can come into a point where insertion sort is often used in scenarios where simplicity, stability, and efficiency is small data set and they're prioritized over a raw speed. So it can also serve as a building block or auxiliary sorting strategy within a larger, algorithms or in combination with other sorting techniques. So, however, for sorting large data sets or in performance critical applications, more efficient sorting algorithms are typically preferred. And overall understanding insertion sort and its strengths and weaknesses on help developers, they make informed decisions about when to use it effectively. So thank you for watching my video. Please do like, share, and subscribe to my YouTube channel and stay tuned for more videos. Thank you.